Hey there.
Hey there. Stephen, how do you pronounce your name? Is it
Angster.
Angster?
Gangster without the G.
Angster without the G. Okay, but Stephen's right for your first name?
Yeah.
Not Stephen. Okay, great. So
Let me see. Why is my volume so low?
you seem loud and clear on this end.
Okay, great.
So has it been a while since you've been down to the field area, like Walla Walla?
Hang on. Sorry, my volume isn't really loud, and they just redid our government computers, and
Oh,
everything's
okay.
all messed up now.
Well, I'll let you concentrate on getting ready.
Okay. Can we try to see if my talk will go? Because I just tried to share a screen in a different program earlier today, and I had to go through
Uh,
all these
I
permissions.
think so. Have you heard anything from Maria in the last few minutes?
No, I
She's the
haven't.
technologist here. I'm not quite sure if you start. I guess we're not being. I don't know what the participants are seeing or hearing. To tell you the truth, um,
Okay.
but let's see. Uh, oh yeah, here she comes.
Hi there. Let me try and get my video going. Oops. Hey there.
Hi,
Hi.
Maria.
Good. So I'm actually Teresa.
Oh, you're Teresa. Yeah, you didn't look like Maria. Okay.
Um, you should be able to share.
Okay.
And are the attendees able to see yet,
I believe so.
or are they? Because Stephen wanted to see if it worked
Oh.
before it's going on.
I believe they can.
Somebody can see.
Yeah, so they're writing in the chat and they say they can
Yeah,
see
yeah.
in here.
But maybe they can see in here. Okay. Yeah, they can see us getting ready.
Yeah.
Well, then perhaps I guess we try it and see if it works and fix it if it doesn't,
Okay.
Stephen.
I'm gonna
But
hit
maybe,
share.
but I was going to introduce you
Oh,
first.
here we go.
Do you want to do that first? Me introduce you.
Hang on. It's asking me to
We
do
still got
my
we still got a
permissions.
couple minutes. It's not even really 7 yet, quite.
Okay, I'm gonna have to quit and reopen. Sorry, I had to go through this earlier today with a different talk, so I'll join you in just a sec.
Okay, great. So see if I can remember you by sight if it's you next time, Teresa.
Yeah. So I'm gonna mute and
Yeah.
my video and I'll let you do guys let yourself do what you
Okay.
need.
Okay. Once he comes back, I'll introduce them and we'll go from there.
Okay.
Thanks.
Yeah.
All right, I'm back. Ooh, this looks promising.
Good. There we go. Okay, so shall I go ahead and give you an introduction? Ooh, nice.
How does that look?
It looks great.
Okay, good.
So shall I introduce you, you think? So,
Yeah, if you're ready.
I suppose. I mean, it's 7. People might still be sitting in their Zoom seat, but there's quite a few here. Um, so, all right. So for the 20 or so that are here, some of you may remember me. I'm Ralph Dawes, and I'm with, and we are the Erratics, which is the Wenatchee chapter of the Ice Age Floods Institute. And I'm kind of sitting in for Brent Kunderla, who I think may be traveling. He's the president of the chapter. Anyway, we are lucky enough to have as a guest Stephan Angers, who's with the U.S. Geological Survey based in the Seattle office. But he's been working in Eastern Washington down towards Walla Walla on a project, which I'm excited about because it's about faults and how active one in particular, or one fault zone perhaps, we'll find out, has been. But also it has something to do with clastic dikes. Some of you have been on some field trips in the past in Eastern Washington with us or with other groups, and you've probably run into some clastic dikes, even looking at the giant glacial flood deposits, glacial lake flood deposits, probably different age, perhaps different origin than the ones that may be related to what Stephan's been working on, but they always raise all kinds of questions. So maybe we'll get some insight into some specific clastic dikes tonight. And then the faults, especially if they're active, I mean, the shape of the landscape here in Eastern Washington, there's the Yakima fold belt with these big folds and faults, and maybe some of them are connected to faults that are still active today. So it's not just old geologic history. So I find that all quite intriguing. So I'm glad I'm here. So without any further ado, because I don't know very much about Stephan's history beyond that he's working for the U.S. Geological Survey, I'm going to give this talk. But I will say that Stephan Angers to talk to us about, the title is Paleoseismic History and Hazards Associated with the Wallula Fault Zone, a new look at clastic dike features in southeastern Washington. And with that, I'll let Stephan take it away.
Right, and sorry for the mouthful of a title. Hi, everyone. Thank you so much for the invitation. I think this has been in the works for a couple of years now, and thanks to COVID, we're virtual, but this is how we work nowadays. So, yeah, my name is Stephan Angers. I work for the Earthquake Hazard Science Center of the USGS, which is mostly based out of the Bay Area in California. But the office that I work out of in Seattle mostly does research and seismic monitoring within the Pacific Northwest. And so our mission is to conduct and monitor earthquakes, conduct research, and monitor earthquakes across the Pacific Northwest that emphasizes an understanding of earthquake hazards of the region, mostly within heavily populated regions near federal, state, and local infrastructure, such as dams. And one of our main products is the National Seismic Hazard Map, which is shown here in the bottom left of my screen here. So this is a project, what I'll be talking about today is a big project that we've been working on the Wallula Fault, trying to understand its seismic hazard potential. And this is a list of colleagues and co-authors that are involved in this. All right, as I'm sure you all are familiar with, the Cascadia subduction zone, which dominates the geologic processes in the Pacific Northwest, but also gives us our nice, beautiful and dramatic landscape to explore. This is a satellite image from NASA, which I love because I think it beautifully shows the distinct landscapes and environments of the major tectonic settings. Over on the western side of the continent, we have the nice green colored forearc of the subduction zone. We have the snow-capped volcanic arc here with our nice volcanoes, and then the dry back arc where the Wallula Fault lies, and what we're going to be talking about, or I'll be talking about, over in eastern Washington. Next slide. So just to back up just a little bit to show why we have active faulting in the Pacific Northwest. Upper plate deformation occurs in response to the locked nature of the subduction zone and the kind of oblique angle that the Juan de Fuca plate subducts underneath North America. So the map on the left here shows the relative velocities of permanent GPS stations within the Western US. So this shows the motion that's driven by the plate boundaries along the Western coastline. And it shows that motion or deformation extends as far east as Salt Lake, shown here in this map by these small little red arrows. And as we move to the west and closer to our plate boundaries where things are really moving, we could see that these arrows get longer, meaning we have faster motions within the upper crust and things are moving. When we go from shorter arrows to longer arrows, that suggests that deformation or some sort of stretching, compression, or strike slip or transform motion is occurring. So there's a whole group of people called geodesists who study this and tell us what's going on. And if we look at the Pacific Northwest in the map on the right, this is a map from a research paper by McCaffrey. He's showing that between, say, the northern border we have with Canada and from Central Oregon, on the western side of the Cascades, we have about 5 millimeters a year of north-south contraction. Back over on the eastern side of the Cascades, there's about 2 millimeters a year of north-south contraction. And the change or the difference in this deformation rate really is because everything in the Pacific Northwest is kind of rotating around in this clockwise position here. So as we go closer in towards the circle, we get smaller velocities. So just in comparison, the San Andreas Fault down to the south in California, that accommodates about 40 millimeters a year, which is about as fast as your fingernail grows. So the motions that we have in the Pacific Northwest are relatively small compared to what's going on further south. All right, so this map shows the active faults within our database at the USGS that are that we know of that are active and accommodating this deformation that's measured within the crust. These faults are color-coded by age, which isn't too important for this talk. But what's important is that the faults here are showing that they generally trend to the northwest and are more or less focused along this narrow zone, which we call the Olympic-Wallala lineament. And I'm not sure. Can someone tell me if you see my arrow? No response? I'll assume you do.
Your cursor arrow, I do, yes.
Okay, great. Yeah, so my arrow is outlining what is called the Olympic-Wallala lineament here. And so it's composed of a mix of thrust, reverse, and strike slip faults, which in my opinion are a little bit more difficult to characterize for seismic hazard. A couple reasons why is that they, for example, thrust faults or reverse could be blind features, meaning they don't reach the surface, and so they are harder for us to see. And then strike slip faults, in the way that they move, deformation or evidence of past movement is harder to preserve. But what we'll be focusing on is the Wallula Fault Zone, which forms the eastern end of the Olympic Wallala lineament and trends across the Columbia Plateau, which is our study area tonight. And of course, can't talk about Eastern Washington and give a talk to the Erratics group without mentioning the Missoula floods, which ravaged and reshaped the landscape of Eastern Washington during the last glaciation. The outburst floods originated from a series of proglacial lakes to the north, shown in green in this map here from Richard Waite, and flowed down across Eastern Washington through these channels shown in brown and back flooded at the Wallula Gap. And these back flooded waters formed Pleistocene Lake Lewis within the Pasco Basin, which was repeatedly filled and drained sometime between about 21,000 and about 14,000 years ago. The deposits left behind from this lake have really been key to our understanding of the seismic history of the Wallula Fault. And these slackwater deposits are commonly known as tushy beds, what are rhythmic beds of sand and silt. So in this picture here at Burlingame Canyon is pretty famous. We could see the nicely stacked tushy beds recording the multiple flood events that inundated this region. While the initial pulse of the floods within the channels was really some of the most energetic phenomena on Earth, the fine grain nature of these deposits, the sand and silt, especially the ones preserved at higher elevations above and out of the channels, indicates that the flood deposition was mostly dominated by a low energy environment. Interbedded within the flood deposits are the tephras, which provide for us key geochronological markers within the tushy beds and give us a sense of time. The ones relevant to this, our study so far are the Mount St. Helens J, which erupted from Mount St. Helens about 15.4 thousand years ago, and Glacier Peak G about 13.5 thousand years ago. And these are interbedded. The Mount St. Helens J is interbedded within the tushy beds, and the Glacier Peak G is actually interbedded within the capping loess, so after the tushy beds. And that age actually provides a minimum age to when the floods ended in this area. Okay, so back to the Wallula Fault. We could see Wallula Gap here, and this whole region to the north, this lower area in Pasco Basin was the back flooded areas of Lake Lewis. So at the surface, the Wallula Fault is comprised of a kind of a 7 to 10 kilometer wide zone of northwest trending faults, fault chord anticlines that manifest as this topographic lineament that trends across the landscape here. And so these structures coincide with a prominent magnetic anomaly in the subsurface that extends uninterrupted for about 120 kilometers, suggesting that this fault zone as a whole and as one is capable of a magnitude 7.5 earthquake. The Wallula Fault has been suspect as a source of the 1936 Milton Freewater earthquake, which is the second largest recorded earthquake in the state of Washington. Given its location relative to the major Tri-Cities area, the McNary Dam, and of course the Hanford site to the north, we really want to know more about the history of rupture on this fault and the hazard that it poses to these areas. So the big question that we're trying to answer is, what is the rupture history and how was it slipping during these past events? So that's really our motivation for our study here. The most comprehensive, what we call a paleoseismic record, is preserved at a fault exposure at Finley Quarry, located west on the west side of the Columbia River. Here, my boss, Brian Sherrod, published a paper in 2016, which identifies at least 3 late Pleistocene surface rupturing earthquakes within the last about 34,000 years, as well as 1 distinct liquefaction event that occurred within the last 10,000 years. This liquefaction event cut across the Glacier Peak G tephra, so that really provides our known age, limiting age of that event. But a lack of rupture at the Finley Quarry site kind of makes the source for this liquefaction remain in question. And that's what we'll be looking at today. So expanding acquisition of airborne-based LiDAR surveys along the northern slope of the Horseheaven Hills here led to the discovery of the Wallula Scarp in east of the Columbia River. And I'll be focusing most of the talk about this feature here. So this is a map this is a LiDAR-based slope shade map showing this new LiDAR data that revealed the Wallula Scarp. And for those of you unfamiliar with LiDAR data or slope shades, this map is showing areas of slope. So steeper slopes are shown as darker regions and flatter areas are shown as white. It's a bit tricky, but it's the best way really that we identify scarps. And I'll be showing them in a couple slides. Traced in red here is a Wallula Scarp that we've mapped out based on the LiDAR. And it's about 20 kilometers long. It parallels the mountain front of the eastern portion of the Horseheaven Hills. And down below is a topographic profile that I've taken across the scarp here. So this is A to A prime. And what this is showing is we come off the slope of the Horseheaven Hills. Here's the north facing escarpment of the main mountain front here. But as we start moving along this flatter surface, there's this little bump, and this inset image up top here shows this feature right here is the Wallula Scarp. So we call this an uphill facing scarp. So in the lower left here, I'm showing a more detailed LiDAR slope shade image of the Wallula Scarp near its western end. This nice trace coming across the image here is the Wallula Scarp, and it cuts across the topography very nicely here. It also splays at this section here up trending to the northwest. And then this is a picture on the right. So I'm trying to link this gas pipeline station actually with this photo. So this photo is looking to the northwest here. And as you can see, it's a little tricky to identify in the landscape. And I think this really shows the power of LiDAR here. that we're able to see very subtle features within the landscape. Moving a little bit further, moving further to the east here along the Wallula Scarp. The scarp crosses this elevated bedrock bench here and starts trending along, and it crosses across these steep gullies, kind of at a rather steep angle, say steeper than a road would. And this photo here is looking at a drainage wall. Here we have the Wallula Scarp actually dipping towards the south here. And at this location, the Wallula Scarp is more well expressed within the eastern wall of this drainage. Within the western wall, I couldn't really find it. So what this is suggesting that there is a sense of possibly left lateral motion along this scarp or left lateral displacement. If we move a little bit further to the east along the scarp and we go into this deeper drainage here, there's actually bedrock faults exposed within the Columbia River basalts below the scarp. So to better understand the origin of this scarp and to see if it is indeed a fault scarp, we dug a big trench across it in 2019 at this location here at its very eastern end. This map to the right here shows our trench site location, and this building here named our trench site, which is the Suck Trench site. And we'll see that that name has many meanings. But we excavated a 90-foot long trench across the scarp, hoping to see some nicely offset tushy beds below the scarp. And to get straight to the point, we did not find any direct evidence of faulting within the underlying sediments. So this is a picture of the eastern wall looking straight at the scarp here that I have labeled in black. And as you may see in the photo, the tushy beds below, kind of these nice light and dark rhythmically bedded sand and silt beds, are continuous underneath the scarp, and they actually dip into the scarp, which is a little bit unintuitive. But one thing we did find in this trench is that we had a lot of liquefaction, mostly manifested within the tushy beds, but mostly at the northern end, we found that this liquefaction extended up into the loess, indicating that we have some sort of Holocene liquefaction event. We had some students from Whitman College come, and of course this made it on Twitter. A trench but no offset. Students looking for evidence of paleo earthquakes by way of offsetted tushy beds near Wallula Gap. All beds are continuous though, but there are some cool clastic dikes in the overlying loess. So that about sums it up. And so here I'm displaying kind of the official log. This is what we generate from these trenches. And I'm listing off our main observations here. So we exposed tushy beds in the L1 loess sequence. We had these large bodies of liquefaction, which are in orange, colored in orange here, that look like they originate within the tushy beds, which are in blues here, and extend into this tan colored loess. So the scarp really appears to be a thickness change within the L1 loess. There's also this gentle monoclinal fold that's expressed within the tushy beds that's right directly below the scarp. And so that kind of accounts for those beds dipping into the scarp. And we think this dipping of beds is associated with the liquefaction here and might be the result of evacuated sediment within the Touchy beds and being redistributed above into the loess, possibly inflating the land here and causing the scarp. There were several types of fractures we identified. These ones in purple here are these silt-filled fractures. However, we found what appeared to be more, I want to say physical or kinematic fractures that we think are related to this folding. So as we fold it, we're extending the top of the fold, so it would fracture the top. And so we think these fractures are related to the folding, which may be related to the liquefaction. And these fractures terminate up against this yellow unit, which is was this laminated silt bed within the loess, which we think is pedogenic in origin. However, we did get one radiocarbon from this trench, which provides it'd be a maximum age to this unit of about 600 years. And since these fractures terminate up against this unit, we're suggesting that the scarp may be less than about 580 years old. So what is a Wallula scarp? Well, it's nice continuous feature. It's uphill facing, which not a lot of geomorphic features do other than fault scarps and some other features. It cuts across steep gullies where we see bedrock faults and has some suggestion of left lateral slip. While the trench didn't provide any direct evidence of faulting, the scarp really appears to be this thickness change within the loess and may be associated with this liquefaction event. So it really smells of a fault. However, we can't directly say that the Wallula scarp is a fault scarp until we find some nice offsets to really show that. But we highly suspect it is. And given its location and maybe the relatively young age and linear nature of this scarp, we find it rather convincing that this scarp might be tied to the 1936 Milton Freewater earthquake. Shown in this black and white beach ball here is the relocated epicenter, which is only 18 kilometers to the east of the scarp. And it actually has a focal mechanism or a sense of motion. It's showing a sense of motion that's consistent with left lateral displacement, what we kind of observed as a suggestion along the scarp. So there was reported ground failure around the epicenter, shown by these photos here. And the missing kind of 18 kilometers in between of this potential rupture is over heavily agricultured land and probably has been erased since. All right, so yeah, we're kind of perplexed on what this Wallula scarp is, but I think we're getting to the conclusion that it is a fault scarp, but we're really intrigued by kind of the liquefaction that we saw within the trench and what it was telling us. So we started driving around the area, and of course there's these nice road cuts of Touchy deposits, and you could see a lot of these clastic dike features, which I'll talk about in a little bit, well, mostly now, but this road cut in particular is one that we honed in on and thought that we could get a little bit better understanding of this liquefaction process that we saw within the trench. So the Touchy road cut exposes Missoula flood deposits, and interbedded within them is this nice tephra that we identified as Mount St. Helens Set J, which is dated at about 13.7 thousand years. So of course, capping the Missoula flood deposits, we have the L1 Lus as well here. One thing I want to point out with this photo, because I think it expresses geologic time so well in the power of erosion. So in the background here, the Horseheaven Hills and the Wallula Fault runs along there. But these Missoula flood deposits, I mean, these were big blanketed deposits that blanketed this whole area. And so since the flood deposits stopped, incision started happening. And so all this incision of the landscape has happened since the end of the floods, which is about 14,000 years. So it's quite dramatic. One famous thing that this outcrop is known for is its dikes, which I know lots of field trips have come here to look at these features. But this outcrop exposes these large sill and dike networks that cross-cut and locally deform the Missoula flood deposits. And they extend at least to the base of the Lus. The cliff faces here are pretty high and precarious, so we weren't able to get a good look up close at the Lus. But these dikes, in this photo and B here in the bottom left, show kind of this general upward kind of network tapering dike that may extend into the Lus, it may not. Let's see, there are these nicely rounded pebbles that can be found within some of the dikes. And some dikes also show this nice tabular cross-bedding of sand and vertically bedded sand and silt that also have these clay and silt linings that kind of separate each of them. So to get a better understanding of the age of these cross-cutting relationships are great, and many people have thought that they're coeval with the Missoula flood deposits. We collected some samples from these dikes for luminescence age analysis with a goal to better understand the source of the sediment within the clastic dike. Here's another kind of photo mosaic on the eastern wall, just showing kind of the broad expanse of these sill and dike networks within the Tushy deposits here. So we use quartz and feldspar-based luminescence age analysis to get at the age of the sediment within the dikes. For those of you unfamiliar with luminescence dating, we're basically dating the age of when the sediment was last exposed to light. And so in this graph up to the left here, it kind of shows how this works. So we have a sediment that's exposed to the nice friendly sun here. And as it's being transported, it's exposed, it's deposited and then buried, and then it starts acquiring a luminescent signal. And through time, this signal accumulates. And the signal is really electrons that are being trapped within the crystal lattices of mostly quartz. So as time goes on, the more and more electrons get trapped within these crystal lattices. And in the lab, we take these samples, expose them to light, and they actually count the electrons that come off of the quartz grains. And through back calculation of how we're able to get a rough estimate of the age of how long the sediment was buried. So looking at the results of our samples, which we collected 4 of, we find that that the results are quite scattered. So this graph here to the right shows these black dots, which is a measurement of these electrons, essentially, or dose, and the density of those. So we get this large scatter within the results, which is expected because these are liquefied deposits. But we're able to look at these age models, and looking at the central age model, we find that the relative age of the samples is about 40 to 100,000 years, which is generally consistent with the Missoula flood deposits. However, there are some outliers in these minimum age models that give us these really young events. And out of all the 4 samples, we get kind of these 3 possible Holocene events. One at about 5,000 to 6,000, one at 2,000, 2,500, one at 2,000. And explaining these young ages is actually quite difficult, and would suggest that there was some resetting event that happened during these times. And there are very few avenues that I could think of to explain these young populations. Either we had a surface resetting event, meaning that sediment from this sample here was somehow transported up to the surface at one of these time periods, reset by the sun, and then brought back down. Or we have somehow sampled or measured a lush sediment that was exposed here and somehow transported back down the dike. So what these results are showing us is that the liquefied sediment, some of it has come from above. However, we have this Mount St. Helens set J that this dike crosscuts. And in some of the samples, the central age model shows that most of the sediment is older than the Mount St. Helens J, suggesting that the sediment came from below. So in the same dike, we're having a mixing of sediments from above and below this Mount St. Helens J. So clastic dikes are common features, of course, distributed around Eastern Washington and have been the subject of several studies that have started with Jenkins back in 1925. Since there have been many mechanisms proposed to explain these features, for which there are several types. The ones observed at the Touchy Road Cut really fall under this type 2 classification that are described in this nice atlas by Fetch and others, who summarize and very methodically analyze each dike type within Eastern Washington, really for the purpose of understanding their origin. And their main observations for these types of dikes are that they're composed of injected flood sediments in moderate to high pressure hydraulic systems, formed sometime during or soon after the late Pleistocene. And the most sensible mechanisms for their emplacement are either by unloading or unloading during the floods, which would be a complex process of the sediment properties and hydraulic conditions, and or seismicity. Well, if I go back a slide here, there's really only one of these processes that I could think of that would explain these younger populations within our samples here. Given that this unloading and unloading during the floods would have had to have happened sometime during the late Pleistocene, these Holocene ages that we're finding within the dike sediments don't really match up to that. And so the alternative here is seismicity. And if let's see if this video works here, I have a possible mechanism. Oh no. Well, I'm sorry, my video is not working. What this was going to show is there are lots of videos on YouTube. If you put in your search, earthquake liquefaction in Japan earthquake, you could find these videos of the land pulsing during these earthquakes. And during the pulsing, we have liquefaction coming up out of the ground, squirting up out of the ground in these geysers. And then as the fracture opens again, it sucks the water back down. And this repeats back and forth several times during a single earthquake. And so that process, I think, could explain why we have vertically oriented, cross-bedded beds within these dikes. It would explain our kind of distribution of ages, the mixing, as well as the young age populations within our OSL results. So we think these are seismically induced clastic dikes. And we could use empirical relations of earthquake magnitude and distance to observe surface liquefaction, determine the size of radius that we need to look for all possible sources of seismic shaking. The Wallula Fault is the most proximal and maybe the most likely source of the liquefaction at the Touchy road cut, which would require only a magnitude 5.5 to produce liquefaction at the Touchy road cut site here. The short distance of the 1936 earthquake over to the east here also makes it a possible source. However, our ages really don't reflect it, and we really don't think that these clastic dikes were formed during the 1936 earthquake, but more likely an older Holocene seismic event. The height in Horsehaven Hills Fault, here's a Horsehaven Hills Fault in the map, and then the height fault further to the south, are within a reasonable distance to be sources to the liquefaction here, but they have not been shown to be Holocene active. Looking at this graph, the furthest away of possible sources would be the Yakima Fold and Thrust Belt. These are Holocene active features that could possibly as well be the source of the liquefaction observed at the Touchy road cut. However, they do require higher magnitude thresholds to produce liquefaction at the Touchy road cut site. So together, our observations kind of allow up to 4 possible Holocene liquefaction events within kind of our study area here. And at least one of these was associated with a rupture on the Wallula Fault, that being the Wallula Scarp. Liquefaction was probably common during earlier to mid Holocene when the hydrodynamic systems were a bit different. The clastic dikes that we observed at the Touchy road cut would require a lot of fluid, and we don't have a lot of fluid today. So something was definitely different. So the Wallula Scarp, if it is in fact a fault scarp, would represent a partial rupture of the 120 kilometer long fault, and gives us a little bit of insight to maybe how the Wallula Fault acts or behaves. However, I think we need to definitely dig another trench across it to first identify when, if it is indeed a fault scarp, and then as well try to kind of hone in on that rupture age. And so based on what we found, I think we do have some plausible evidence that the Wallula Scarp is likely the rupture trace to the 1936 Milton Freewater rupture. But more to come on this, as we're still doing some other investigations on the Wallula Fault. We are collecting and acquiring some more geophysical data to better understand this fault structure in the subsurface. How this fault moves kind of relays into seismic hazard analysis and helps with predictions of ground motions and everything. So that's all I have for tonight, and I'm happy to take any questions. I'll turn on my chat and apologize as my sound isn't very loud, so I'll try to listen in as hard as I can.
Steve, thank you for, first of all, I mean,
Thank you.
I have a question. I think I ended up confused. So it's possible that the scarp is a ruptured trace from the 1936 Milton Freewater earthquake, it says. But were you saying you don't think that was a liquefaction classic dike producing earthquake? Or what is it?
So in the Brown report, which is the paper showing, which is a paper that had the photos of the ground rupture and everything, there were reports of liquefaction within kind of the Walla Walla Basin area. I know some farmers reported that their wells either turned off or turned on, and that there was some form of liquefaction that bubbled up within the basin. Where the Touchy road cut is, it's at a higher elevation. And I don't think experienced any.
Okay, so all right, so like with those
liquefaction
ages
during
you
that
got
time.
from the luminescence, that's over at the road cut a little ways away. Okay, and higher up. So
What was that? Sorry.
that was based on the luminescence ages coming from the Touchy road cut, which is a few kilometers away and and up above the bottom of the basin, like you said. There's been all that incision since then. So okay, so there still was liquefaction apparently in 1936, but not high up there in the Touchy beds.
Right. What I think's being recorded at the Touchy road cut, based on our luminescence ages, is I think we're seeing, we're recording some other Holocene seismicity that affected that area. Whether or not it's from the Wallula Fault, we're unsure, as it's hard to identify the source there. We don't think it's 36, but we think it's sometime during the Holocene. And what I was trying to show with that photo and kind of emphasize the incision is that there's been a lot of incision that happened in that area since the end of the floods. And as that kind of incision happened, we're lowering the groundwater table and changing the hydrodynamics. So the earthquake could have happened anytime in between there. Thus would have, being the water table would have been higher at that time and would have had the nice source of water to produce these large dike features.
Okay, I see. Thanks. Anybody else? So just checking now, there's thought of going back for more trenching possibly, is that?
Yeah, if I back up, I could show you where we're going, where we'd like to go. Actually, we need to get permission from the landowner. Yeah, it's kind of on this bedrock bench here. I want to, as much as I love the Tushy deposits, because they're this nice barcode record that we hope to be offset, they're not so nice because they're really prone to liquefaction. So even though we're not completely out of the Tushy bed deposits up on this bench, we did walk across this area and I did see some alluvial fan sediments, which are a bit coarser and a little bit more common, a more common deposit to trench in per se. And I hope that we find a little bit different environment up there depositionally.
Okay. See, it's weird. It's like, I don't know, I'm speculating. It's somehow possible the Tushy beds where you did trench, they behave plastically with the water in them during, if there was a fault developing, a scarp developing on an
Yeah, it's really hard to explain the scarp at the trench site. And I think it's a result of, it was just a bad trench site, which I kind of like the name Suck Trench. Yeah, maybe if we moved, a foot over, if we dug a little bit further, it would, you never know in a trench. You're always digging to find something clear. But yeah, I think the scarp is related to some movement through liquefaction of the Missoula flood sediments, just at the trench site. I don't think it happened like that along the entire scarp. I don't know of any other feature. The whole scarp is manifested within the loess, as I showed. It's just that thickness change. And loess is an aeolian deposit, and there's no wind deposit that I know of that would form such feature for so long and so continuous and linear. So yeah, we just need to dig another trench, really. I see a question in the chat. What was the intensity of the earthquake? I assume you're referring to the 1936, which was magnitude 6.
And you think that scarp may be from the same earthquake? So,
sorry?
You think the scarp that shows up in the LiDAR, you think that may be from the same, it might, you still think it might be from that earthquake, 1936?
Yeah, I think based on our observations on the ground, the possible sense of left lateral motion matches up with what people have kind of put forth as a mechanism for that earthquake. That matches up. It's on trend. It's not too far away. There's only 20 kilometers in between. So if you add, so it's already a 20-kilometer long scarp. And if you add another 20 and you do some empirical relations, a 40-kilometer long fault would produce a 6.0 earthquake. So everything's kind of lining up. However, the scarp kind of disappears within the LiDAR as it heads into the Walla Walla Basin area and crosses all the farmland. It's probably dug up.
When Sharon and others were there earlier, did they not have the same LiDAR?
Like at the Finley Quarry study?
Yeah.
They didn't have the LiDAR that I'm showing here, which extends east across the eastward on the other side of the Columbia River. It chopped off somewhere in one of their figures in the paper. You could actually see it, and Brian did see it before, but it wasn't until the state acquired the rest of the LiDAR that we understood the length and, okay, this is likely a fault scarp. I see another question. Do these findings have implications for nearby Dam or Hanford? Yes, and that's what we're trying to do here with understanding the seismic history of this fault. With understanding the history, we get a reoccurrence interval on faults, which tells us when it's next likely to rupture. Understanding how big these ruptures are tells us its potential. And we could feed this data to ground motion modelers who could put this and run this data through a model and tell us what shaking intensities the dam or Hanford could expect. And so that's the purpose of our studies here.
Wow. It's really applied for hazard consideration.
Any more questions? I could back up and re-show slides, or was anything unclear?
I must say, I gotta look at those videos myself still, but the idea that liquefaction can go up and down in one event, one seismic event.
Yeah, yeah, I'm really disappointed those videos didn't work, because that was kind of the culmination of this talk. It was partly to explain the title of a new look at clastic dikes. I think it should be a process considered as it's related to seismicity, but it's a process to explain our age results and the sedimentary structures and characteristics that we observe at the Touchy road cut. I don't think this is what is called sloshing explains all the clastic dikes in Eastern Washington. It's just the ones that we saw at this Touchy road cut, I think could be the result of these fractures opening and closing as seismic waves kind of pass through the land. The land bubbles. A lot of people say it being an earthquake feels like being on a boat. You rock back and forth, and those are the waves crossing through the landscape. And so if you do fracture the land, they're going to open and close as those waves go through. And if you add water to that, it's going to push and suck back down sediment and water.
Okay, well, I have one last question. Most of the ages suggest, what do you think that would also have been seismicity before 10,000 or whatever years ago, the older, like that central age area of the luminescence ages?
Let's go back to the age figure here. So say again.
Well, did it suggest there were, so you have some minimum ages, but there's a range of older ages before 10.1
right.
thousand years ago. Do you think the older ones were also ages of liquefactions?
No, so I'm sorry. I don't think I explained this slide too well. So the luminescence age is telling us when these sediments were buried or deposited per se. We sampled liquefied sediments. So these are, I think, the central age model, this 40 to 10,000, is within range of the Missoula floods. So meaning we have Missoula flood deposits sourcing the sediment to these clastic dikes. That's all that's telling us about the central age model. It's this minimum age, kind of these outliers that are hard to explain. How do we get a grain that was reset 5,000, 2,000 years ago? We're about 20 meters below the surface here, within the kind of at the same level as Missoula flood deposits. So the question is, how do you get that grain back down there? What's the process involved in that? And that had to have happened at that age. So that age is a minimum age of that event,
I see. It's kind
right?
of, yeah, this may not make sense to everybody, but it's kind of like doing zircon ages in sandstone. The youngest ages are the minimum, or no, the maximum.
So
Anyway, yeah, in this case, yeah. So it puts an age limit on it. The youngest ages of sediment of when sediment was exposed in there. That I'm catching it. I can't explain it well, but now I understand better what you're saying.
you understand it?
Yeah.
Okay.
You're the one
Yeah.
who can explain
And
it.
if I go back one more, the dikes that we sampled, and I didn't point this out, and I'm sorry, the dikes that we sampled, we specifically sampled dikes that cross-cut the Mount St. Helens J. So based on that relationship, we know the dike is younger than 13,000. The question is, so that means if this dike, say, opened from above, then all that sediment should be younger than 13,000. In our age results, we found sediment that's actually older than the Mount St. Helens J. So that suggests that sediment came up from below. But also within that same dike, in that same sample, we have younger sediments that are 2,000 years in age. So that came from above. So it's a mix of sediments, but to explain these younger ones, and these younger ones actually provide kind of the youngest age of that event, of that liquefaction event.
Okay, that makes sense to me now. Okay, by the way, does Sky Cooley used to work on stuff like this? I don't know if you know him. Did he ever
Can you say that louder? I heard Sky
a guy named Sky Cooley used to work on plastic dikes when he was at Boise State.
Yeah, yep.
Did he ever come by, or did you ever talk to him about this?
He was curious about our trench, and I know I've kind of read some of his stuff, and reading a lot of the clastic dike stuff. They say, none of it goes up into the L1 less. However, it was quite clear in the trench that it did. There was a very sharp textural contrast between the liquefied sediments within the flame structures in the loess compared to the, nice massive loess. So that was real, that it extended up into the loess. And that's what got us, to the Tushy road cut and wanting to know really the age of the liquefaction in these really big dikes, which could possibly be the plumbing system to what we saw in the trench.
So that bottom left figure B on that slide you have now, that has the dike at least dotted or dashed is going up, the classic dike going up into the loess.
Yeah, I dashed it because it's hard to say. I didn't hang off the cliff there to really look. They're pretty soft and precarious, so I couldn't get that close to tell. Yeah, it's hard to say. There was a case in this next slide. Yeah, here I point out a deformed basal loess contact. This is right above a very large dike. I don't know if you could see it in the photo here. The dikes are this nice light color. The Tushy beds are these kind of redder, orange, tan bedded units. There's actually these big, large pebbles and cobbles up here, which I don't know. I really want to sample those, but I don't know how to explain those in the loess, but they're there. But they're too hard to sample because it's a pretty high cliff face there.
Yeah.
But I think, the general sense of these dikes is that it was pretty, I think, high pressurized fluid system. And you had some interesting forces going on and a lot of movement of sediment during the time that they formed.
Wow.
And they look pretty fluid based on their stratigraphic properties. I don't think it's dry deposition falling in.
Well, I want to thank you again. I'm sure everyone else, I speak for everyone here. Is it possible to date? Wait, there's another one more.
Yeah. Is it possible to date the base of the loess? Yeah. One conclusion that I forgot to mention, and is that so between the two sites, between the trench site and the Touchy outcrop, we had two tephras. Let me go back. So we have the Mount St. Helens J within the Touchy road cut, and that's interbedded within the Missoula flood deposits. So that's 13.7. In the trench, we have the Glacier Peak G, which was just in the capping loess. So that provides minimum age to the flood deposits. And so that's 13.5. And this is 13.7 within the flood deposits. So it's sometime in between there, the floods ended. And so let's call it 13.6. And so that's actually 1,000 years later than what prior estimates have by the Benito and O'Connor paper, which is the only paper I could find within the region that provides the youngest date of Missoula flood deposits. So can we date the base of the loess? Not really. We could apply OSL, but we always have the problem of burrowing animals and sucking in kind of modern sediment. So you always have that uncertainty with sampling so close to the surface. But what we can do is constrain the age or the onset of the loess by these tephras.
Wow.
Tom, can I help sample the upper bands? Sure. Yeah, we like volunteers. I don't know if my email was advertised, but if you're ever interested in volunteering with us, I love help. One of our co-authors, John Lasher, is a local geologist in Kittitas Valley up in Ellensburg. So he helped out a lot with this study and a lot of other ones that we do. All right,
Excellent.
Tom, I got your email. Any other questions?
Well, I guess the time is good for wrapping it up then. This was really, provided a lot more new information that I didn't know was out there. So that's.
Okay, good. I'm glad you learned something.
Oh, yeah. Now I want to go down there and look at this Touchy road cut.
Yeah, it's a good one. You just got to be careful of the cars coming by because it's a pretty narrow road there, and the walls are always collapsing, so they're always revealing something new.
Yeah.
They're pretty soft.
Risky. Yeah. Maybe in the spring or summer. Plus, there's nice wineries in the area.
Oh, there's a question. What highway is the Touchy road cut? Sorry, I don't know off the top of my head. It's the road. It's the only road that heads north out of the town of Touchy. There's a gas station there, right on the corner, and just go north on that road for about 2 miles, and then you'll see the road cut.
So that view is looking kind of to the south or southwest.
This view is looking, to the southwest. So that's, the Horseheaven Hills, and you can see the big windmills in the landscape there. But it's almost directly north of the town of Touchy.
Cool. Well, one thing about these Zoom meetings like this is you don't get to hear the clapping. So
yeah, it's okay. I'm used to it now.
Yeah. Thanks again. We really appreciate it.
Yeah, you're welcome. Thanks, Ralph.
Yeah, I see the clap, clap. Okay.
Have a good night, everyone.
Thanks again, Steve.
Yep.
Bye, everybody.
Bye, Ralph.